Hey everyone, thanks for tuning into this video. Today we're just going to explore some different examples of working with ionic compounds. There's a few different ways we can tackle problems like this, but I'm just going to lay out a step-by-step kind of solution on how you can go from a name of a compound to the particular atoms that are involved in it, and from the atoms to the names, and then also how we can draw out our Bohr-Rutherford diagrams to help us explain or prove why this ionic compound makes sense. So the first example we're going to look at is the question asking, what is the molecular formula of magnesium chloride? So here the question's asking for a molecular formula and it's giving us the name of the ionic compound. So step one, to help us figure this out, is we have to figure out what elements are involved, because it hasn't given us, it gave us the name, but it doesn't really give us like what exact precise atoms we're going to use. It's easy to figure out, but we'll just do this as step one. So what are the elements involved? So we have magnesium chloride as the name, and that tells us that magnesium, it's the exact same name as the element itself, is the first one, and chlorine is going to be the second one. We know that when we're naming ionic compounds, we add that IDE ending here. So we know that we're working with chlorine. And another part of this step that we're also going to do is just determine which one of these elements is the metal and which one is the non-metal, or in other words, which one is the cation and which one is the anion. So if we look over here at our periodic table, magnesium is over here. It's a metal because it's on the left side of this staircase here. And then we have chlorine, which is over here. It's a non-metal. And so let's just go back to our problem, and we're going to label magnesium as the metal. Otherwise, it's going to be called the cation because it's going to give away its 2 electrons. And then chlorine over here is the non-metal. It's going to become the anion because chlorine has 7 valence electrons, which means it's only going to accept 1 electron to have a full shell. Okay, so that's step 1. Next, let's go to step 2 here. Step 2 is determine the ionic charges. Determine the ionic charges. So we have magnesium and we have chlorine. If we go back to our table here, so magnesium is in group number 2, which means it has 2 valence electrons. So we know that it's going to give away 2 electrons because that's easier than accepting 6. And when you give away 2 negatives, you end up with a positive. So magnesium is going to be positive 2. Then we have chlorine over here, 7 valence electrons, because it's in group 17. And so chlorine is going to have a charge of -1 because it needs to gain 1 electron or gain a negative in order to have that full 8 shell. So we go back over to our problem that we're determining the charges, and we know that magnesium, based on what we just decided, is going to have +2. Chlorine is going to become a -1. So step 3 is what we're going to call drop and swap. And we are going to take these charges here and here, drop and swap, meaning that we get Mg1 Cl2. When you drop and swap, you can just lose the charges because this is telling us how many atoms we're going to have of each. How many atoms of each element. So how many magnesiums are we going to have and how many chlorines are we going to have to make magnesium chloride? So this magnesium 1, chlorine 2, we never have to say 1. Anytime there's a 1 here, we can just cross that out because if it says Mg, magnesium, we know there has to be at least 1. So if there's nothing there, then we can assume 1. So the correct way to write it is MgCl2. And that, my friends, is our final answer for the molecular formula. Molecular formula for magnesium chloride. That's how we did it. So obviously these 3 steps are a little bit involved. The faster you get at this and the more understanding you have of the periodic table, the easier it'll be to do this. But in the meantime, if you feel like it's tricky to go between molecular formula to the name to finding out the ions, then this is a good 1, 2, 3 step to do in order to figure it out. Now we're going to go even deeper into this kind of example of magnesium chloride, and we're going to prove it. Why is it 2 magnesiums for every 1 chlorine? Because saying, oh, I just drop and swapped, that's not really a proof. That's a technique that we can use to figure it out, but that doesn't tell us why is there only 1 magnesium and only 2 chlorines. Why? So a good way for you to prove this would be to explain to me that magnesium, we know, has a charge of 2+, and chlorine has a charge of -1. And this 2 here tells us that there are 2 chlorines. So we can write it, like this. So on one side we have 2 plus charge for 1 magnesium. We have -1 for chlorines, but we have 2 chlorines according to our formula. And then we can say, okay, so this side has 2 positive charges, this side has -1 and a -1, which equals a -2. So we know for sure that an ionic compound has to have equal charges. It's neutral. This chlorine, this MgCl, doesn't have a minus up here. Like, it is neutral. So this, no, it's neutral. So that means that the charges for the magnesium and the charges from the chlorines have to equal 0. So this could be your proof here that this formula is right, because 2 negatives from the chlorine and 2 positives from 1 magnesium, they equal each other. So we need to have equal charges. Another way that you could prove it is by drawing it out. So let's use our Bohr-Rutherford diagrams here. So we have magnesium. Let's just draw this guy out. So magnesium has 2 valence electrons. Let's do them in a different color. And then we have 2 chlorines, right? So according to our formula, there's 1 magnesium and there's 2 chlorines. And we can always look at our periodic table to figure out how many electrons we have. We're going to 2 chlorines. And we know that each chlorine is going to have 7 valence electrons. Since we already discussed that, awesome. Let's make chlorines valence electrons yellow as well. Okay, so if these 3 are going to bond together, because that is what our formula way up there is telling us. It's saying we have 1 magnesium, 2 chlorines, they create an ionic bond. So we can explain this by saying, easy, so magnesium has 2 valence electrons to give. It can give 1 to chlorine. Perfect. Now this chlorine is full, 8 valence electrons. It can give the other one to this chlorine. This chlorine now has 8 valence electrons. Perfect. And this magnesium now loses this outer shell, and it also has 8 valence electrons, because now it just has these 2 shells here. And it will just lose that outer shell because it doesn't have any electrons on that shell anymore, so that shell doesn't exist. So this is another way that we could prove it. So one way to prove it is just by kind of doing the math and saying we have 2 positive charges, 2 negative charges. That's how I know that the formula is right, because we know for ionic formulas the charges always have to equal 0 because the compound itself is neutral, meaning it doesn't have a charge. Another way that you can prove it is by drawing it out and showing me that each of these electrons for magnesium gets donated to 1 chlorine each, and in order for everyone to be happy, we need 1 magnesium and 2 chlorines. Okay, so now that we are getting the hang of this, let's try another one just to test our knowledge. So let's do example B. Right. That is not how you spell formula. Formula. Alright, write the molecular formula for aluminum oxide. So again, here we're given the name aluminum oxide, and we're asked for the molecular formula, which is going to look like this, like the MgCl2. That's the molecular formula. Okay, I'm going to erase that because these are 2 different questions, but that's what the goal is, to get that MgCl2 or Al and O. We're going to figure that out. So step 1, we said we need to figure out what are the elements involved. So here, aluminum, perfect, and the oxygen. So those are the symbols for aluminum and oxygen. And now we can also at this point determine which is going to be the cation and which is going to be the anion. So let's go back to our periodic table, and aluminum is way over here. It's in group 13, so it has 3 valence electrons. Let's erase all our other stuff here, because we're not looking at magnesium anymore. Okay. So 3 valence electrons for aluminum, and then we have oxygen, which, oops, I covered up the group. Then we have oxygen here, which is in group 16, so it has 6 valence electrons. This is my key for electrons, by the way. It's E and then a little negative, and if I'm saying electrons, sometimes I'll add an S at the end, like E's, electrons. That's just a side note, but just in case that was confusing anyone. So 3 valence electrons and 6 valence electrons. Aluminum is going to give away 3, because that's easier than gaining 5. And oxygen is going to accept 2, because that's easier than getting rid of 6. Okay? So, because aluminum is our metal here, let's just say that this is going to be our cation, because it's going to give away, which means it's going to be positive. And oxygen is our anion, because it's going to accept 2 negative electrons. Okay, step 2 is determine the ionic charges. So we have our 2 elements. We know which one is going to give electrons and which one is going to accept electrons. So now we just need to determine how many are each of them going to give away and accept. So aluminum has 3, it's easier to give 3 than it is to take 5, because we're trying to make 8. So if you give 3 negatives, you become positive, and by a factor of 3. So you're giving away 3 negative things, so you're going to become positive 3. Oxygen, on the other hand, is going to accept 2, so it's going to gain 2 negatives, so it's going to be 2 minus. So these are their charges. And that makes sense, right? Because we said that this is going to be the cation, which means cation means positive, and anion means negative. So even if the give and accepting of negative is kind of tricky, as long as you know that the metal is going to be the cation, the non-metal is going to be the anion, then you can figure out which one is going to be positive and which one is going to be negative, even if you have kind of a hard time with the whole giving negatives idea. Okay, so we have our charges here. The next step is going to be drop and swap. So we have our 3 and we have our 2. Remember, we don't need to add the positives and negatives when we're dropping and swapping, just because this is telling us how many atoms of each we're going to have. So aluminum, 2, oxygen, 3. So according to the drop and swap method, we need 2 aluminums for every 3 oxygens. So 2, we need 2 aluminums for every 3 oxygens for this to make sense. For the compound, the ionic compound, to be neutral and stable, and every atom to be happy and have a full octet, we need 2 aluminums, 3 oxygens. Now this is the fun part, when your teacher says, prove it to me. Prove it. Okay, so now we're going to prove it. So we'll do the first kind of way to prove it, and it's to show how the total charges equals 0. So the positive charge equals negative charge. And we remember up here that aluminum is the positive and oxygen is the negative. So all of the aluminum charges have to equal all of the oxygen's charges. So according to our formula, which is really our final answer, write the molecular formula. Okay, this is it. It's Al2O3. But if we want to prove that, then we can say, okay, this tells us there are 2 aluminums in this compound. So, and aluminum has a charge of 3+, so equals 3 oxygens, and each oxygen has a charge of -2. So we're comparing the charges here, right? Then we can do +3 and +3 equals -2 and -2 and -2. And lo and behold, we get 6 positives and 6 negatives. Perfect. That's exactly what we want, because it means we have the same number of positives and the same number of negatives in this ion, which tells us that it's neutral, it's perfect, all of the atoms are going to be happy. If you want to take this one step further, you can draw out the Bohr diagrams for aluminum and oxygen, and you can show how you need 2 aluminums and you need 3 oxygens for enough electrons to be donated and accepted for everyone to have a full octet. So this kind of picture that I found online can help visualize the total neutral charge a little bit easier, I think, than drawing out all the Bohr-Rutherford diagrams, if this makes sense as a different visual. So each of aluminum's kind of like gray lines here is showing the electrons its positive charge. So aluminum is +3, right? So these 1, 2, 3 kind of shows its +3 charges. The oxygen, these two kind of lines that it has are representing its -2, right? So then we can say that it makes sense that there are 2 aluminums and 3 oxygens, because then all of their charges can balance out each other. So this oxygen is -2, this aluminum is +3. It's the same with all of them, but this here is showing how all of these atoms bond together and how their charges balance out, right? Their charges are balancing out because for every 2 negatives that oxygen has, the aluminum has 2, and you can see that they just balance out this way. If this little part is confusing, you can completely ignore this. This is just another way to visualize how it is a neutral atom. 6 charges that are positive, 6 negatives from the aluminum and the oxygen, and that is how we get a neutral compound, which is the goal.